Hello, today I'm going to show you how to solve this problem using a max heap. So what we need to do is take our input, our stones, and we're going to smash two of them together. So if they're equal, they're both destroyed. And if there's a remainder, we have to put that remainder back into the input and keep running it until there's only one element left. And then we just have to return that element. Here is our solution. So the first thing I want to talk about is how LeetCode under the hood here is importing this package, and we're able to use all of these methods from the package um, inside of LeetCode without importing it. So that was confusing. You don't need to do this, but as a result of that, we can create a max heap very easily. We don't have to code it from scratch. All we do is call new max priority queue, which is a function in here. All right, and that will create a max heap for us. And then we just need to insert the values, okay? And by the way, max priority queue and max heap are like the same exact thing. So then we're just gonna insert the values, each stone from our stones input into the max heap. And this is what we get. It's a binary search tree with the smaller values on the left, the larger ones on the right. The next thing we need to do is compare the two largest values in our max heap. So as you can imagine, we're going to pop off this root one. We're going to that's the dequeue function. And in this package, when you enqueue stuff or push it into the max heap, it adds it as an object with a priority and element property. We need the element property, which is the value. So make sure you remember to use dot element. So we're going to dequeue this. Becomes our first. Then this entire side, this 7 slides up, and we can move this 2 as well. Then we're going to dequeue this like that. That becomes second. 4 is going to move up just like that, and then these two values as well. So our new max priority queue looks like this. It looks a little bit strange, sorry, but then we're going to take the difference of these two, right? If first is greater than second, which it is, we take the remainder of first minus second and we add it back in. So that would be another 1. So we'd add another 1 down here and draw the line. Okay, and there's one edge case. If the size of the tree is 0, and we call this front function, it's going to have an error. So in the case of like the last two elements in the max tree are ones, 1 minus 1 is 0, so the tree would be empty. If it is, we just have to return 0. Otherwise, we just return the last element. And that's it. As far as time complexity, the process of creating the max heap is n times log n. Um, so we're just going to simplify that to n. And then also the process of dequeuing it is log of n. And you can find that in the documentation. This is it right here. And for the space complexity, creating a max heap is going to be, we're creating it for the size of our input stones, which is n, so O of n. Let's step through the algorithm now. So the first step is going to look just like I described before. We pop off our largest value, which is 8, and then we pop off, this one slides up, right? Then we pop this one off because it's our second largest. We take the difference of these two, which is 1. Let me just correct this. 4 gets moved up here. The 1 is going to go over here. This one is going to be under here, like that. And so we're going to take the difference between 8 and 7, which is 1. So we're going to add another 1 down here. We'll put an arrow in, and that completes our first step. So now we're going to restart our loop because the max heap size right now is 5. The second loop looks like this. Our max heap is 4211. 1. And we're going to have to pop off our first largest value, which is 4. And then our second largest value, well, this is going to shift up here. And we're going to pop it off. And just like that, it's 2. We're going to have to take the difference of these two, which is 2. So I can put 2 back here. And that's our new max heap. Step 2 complete. Third loop, our tree size is 4. So we need to keep going. So we're going to pop off the largest value, 2. And the second largest value, 1. And we're going to take the remainder of those, which is just 1, and we'll put it back. And look at that. Our tree is getting smaller every step. Now we have 3 ones left. For the fourth loop, our tree size is 3, so we keep going. We pop off our two largest values, 1 and 1. We take the difference, which is 0, which means our root is now 1, and we can simply return that in our last step because we've reached here and we just go down here. Size isn't 0, so we return our front element 1, and that is our answer.